Hello, my name is Amitabh Tripathi and I've been a faculty member with the Department of Mathematics at IIT Delhi for over 3 decades now. Welcome to this video where I would like to share this curiosity about the decimal expansion of proper fractions that do not terminate. I would like to go back a little bit into the history of this discovery. Sometime in the beginning of 1976, when I was still in high school, we were visited by a senior government official of our school. He addressed the students of class 10 and 11 and explained one of the curiosities that I'm going to mention just now in this video. As I recall, he took the decimal expansion of 7 by 19 and, to my amazement, wrote down the digits from right to left, explaining the procedure he went through. I never got to see him then or even later, and the source of his discovery will forever remain a mystery. Some 30 years later, while I was doing some other piece of work, I happened to think about this problem one more time and was very surprised when I was able to unravel the mathematics behind that discovery of his, and in fact the entire discovery that I'm going to reveal in this video. I wish to share with you a method to determine the decimal expansion of proper fractions where the decimal expansion does not terminate. A decimal expansion of 1 by p, where p is a prime different from 2 and 5, is always recurring after the decimal. The method that I'm going to describe to you consists of two parts. In the first part, I deal with denominators that end with 1, 3, 7 or 9. In the second part, we deal with denominators that end with any of the other 6 digits. In the first part, where the denominators end with 1, 3, 7 or 9, I explain what the starting digit is. The starting digit is the digit which appears at the rightmost, and then I describe a method to determine in a sequence the digits that appear from right to left. This procedure will terminate once there's a repetition of the sequence of digits at the start. Consider, for instance, the first part where I deal with denominators ending in 1, 3, 7 or 9. I will explain what the starting digit is, the digit that you start with at the rightmost place, and explain how to get the sequence of digits from there. For denominators that end in 1, the starting digit is 9. For those that end in 9, the starting digit is 1. For denominators that end in 3 or 7, the starting digit is 3 or 7 respectively. Subsequent digits are determined by what I call a multiplying factor. The multiplying factor is determined as follows. Take the denominator and multiply by the starting digit. This number necessarily ends in a 9. Add 1 to this product and divide by 10. This is the multiplying factor. Let's take the example of 1 by 17. The starting digit is 7 and the multiplying factor is 17 multiplied by 7, which is 119, plus 1, divided by 10, which is 12. Therefore, we write 7 followed by 7 times 12 with the carryover, and so on. Let's take another example where the numerator is not 1. Consider 4 by 13. For 1 by 13, the starting digit would be 3 and the multiplying factor would be 4. For 4 by 13, the starting digit would be 3 times 4, which is 12, with the carryover 1 and the same multiplying factor which was there for 1 by 13, namely 4. So I have described for you how I start the sequence and how to proceed with the sequence by using the appropriate multiplying factor. There is no simple way to say when the sequence will terminate. In other words, the number of digits after which the termination will occur. Therefore, one has to rely on a recurrence of the pattern that we started with. In the first part, we dealt with the situation where the denominator ended in 1, 3, 7 or 9. These are numbers that share a highest common factor 1 with 10. For the second part, we'll deal with the remaining cases. The denominators in these cases can be written as a power of 2 multiplied by a power of 5 multiplied by a number greater than 1 and that ends in 1, 3, 7 or 9. The idea in the second part is to reduce the computation to one that leads to the first part. So when the denominator is a power of 2 multiplied by a power of 5 multiplied by something that ends in 1, 3, 7 or 9, we will multiply by an appropriate power of 2 or a power of 5 so that the denominator has a power of 10 in it multiplied by the same number as before that ended in 1, 3, 7 or 9. For fractions between 0 and 1 with denominator 19, there are 18 possibilities for the numerator. Corresponding to each of these possibilities, there is a unique starting point on the circle. The expansion of 7 by 19 has 18 digits after the decimal. There are denominators such as 13 where the number of digits after the decimal is not 12. In fact, if you look at the expansion of 4 by 13, the number of digits is 6. On the other hand, there are 12 possibilities for the numerator when the denominator is 13. So in situations like this, we require 2 circles to capture all the possibilities for the numerator with denominator 13, with a unique starting point for each numerator on one or the other circle. There are cases where we need more than 2 circles to capture each of the numerators. For example, for the numerator 127, we require 3 circles. Some of you may recall from the teaser the property of 9s exhibited by the fraction 7 by 19. In fact, the decimal expansion of 1 over p, where p is prime and greater than 5, has this property that if the decimal expansion of 1 over p has an even number of digits that is repeating, and if we break up these digits into 2 equal blocks and add, you get only 9s. There are numbers other than primes that exhibit the same property, for example 77, and there are numbers that are not primes that do not exhibit this property, for example 21. A more general result that characterizes this property of 9s is given by the following statement. Supposing the decimal expansion of 1 over n has a period with length L and L is even, then 1 by n has a property of 9s precisely when n divides 10 to the power of L over 2 plus 1. If you're curious to know the mathematics behind the algorithm that I have described to you in this video, please see the link in the description at the end of this video.